Amir was giving a very good introduction about quantum mechanics and made my life way easier. During history, humans have always been curious about the surrounding, about how the nature is working, and there has been so many questions about it, like the galaxy, the star, like how to make fire. And following those curiosity and finding the answer for those questions, it led into discovering science, where we can put things in the equation and have a prediction about the nature, how we can formulate the behavior of nature. When the science advanced, then we were thinking, okay, we know how the nature is working, how we can invent new things that never existed before. And that led into building technology. Once we have that technology, then we have more power to look around, do the computation, do things that we were not capable of doing that before, and then maybe build new tools like microscope. And with building new tools, we are able to see things that we were not able to see and observe in the past. And therefore, we ask more questions, and then the cycle goes on and on. And it's been always like that over the past centuries. This is something that happened to physics as well. During the 19th century, there were so many experiments that were not making sense according to our previous knowledge. And people started asking questions, why things are behaving like that? And then people come up with a new theory called quantum mechanics that was explaining things very well. Here is where the curiosity led into science. Okay, what is quantum mechanics? I want to teach you quantum mechanics in 2 slides. When we talk about classical world, we're talking about ordinary size and ordinary speed. But by ordinary, it could be from the size of a micro inside your body to the size of the galaxy. These are all ordinary in the classical world. And you can use Newton's law to formulate the behavior of classical system. If you know, for example, the location of a car, and if you know what forces are applied on that car, following this Newton equation, you can predict what will happen in the future. And these are all deterministic. The difference in the quantum world is that this equation doesn't hold anymore. We have a statistical knowledge about system. When you have an electron, you can't say that the electron is here or there or there. There is some probability. There's a wave function associated with that quantum particle. And all you can talk about is not the location of the electron, is the probability of the existence of electron here or there. And then the equation is not the Newton law anymore, it's the so-called Schrödinger equation. In the Schrödinger equation, what we are predicting is the dynamic of our knowledge, of our statistical knowledge. And for that, we need to know energy of the system, how the system is interacting with this environment. Okay, and quantum mechanics has some awkward and weird features that we've never seen it in a classical world, like coherence, like entanglement, non-locality, wave particle duality. Like, you've heard about this, and Amir gave a talk, like extensive explanation about this, so I'm not going to talk about it now. I just make a quick point about this statistical knowledge, and then I move on. When we describe the state of knowledge that we have about quantum particle with a density matrix rho, if that density matrix, if it was just probabilities, then we would have just diagonal elements, and it's a statistical mixture, right? And it wouldn't be much different from the statistical physics that we know in the classical world, right? But the difference here is that we have some off-diagonal elements, which tells you that the probabilities are actually correlated. And this is something that doesn't have any classical counterpart. This, in Amir's language, this is the superposition that he talked about. Okay, you all got a PhD in physics and quantum mechanics, and you're ready to build technology. You have the science, and you want to make advantage of our science and build technology with that. You want to do quantum algorithm. How crazy we are. Well, this is something that we always do, right? When we send a rocket to the space, what we do is that we use the Newton law. We say, okay, we make those forces such a way that the system behaves the way I want it to be. So this is the way we control the stuff. And we want to do the same thing with Schrödinger equation. We suppose that I can encode information in the matrix rho 0. If I could engineer the interaction of my particle with the environment, with the Hamiltonian that we have there, by applying microwave, optical forces, anything that we can, then we can engineer the system to behave in a certain way and evolve to a certain density matrix. This is the way we do computation with that. And because it's a naive generalization to go from the bit, classical bit, to quantum bit, I talk about a two-level system that is more common use, but it is not the only way that we can store information. So instead of a bit, classical bit 0 and 1, we think about the two-level system that can be either in the ground or in the excited state. And that's the initialization, where we have the ability to prepare a quantum system either in this state or in the other state. Then we assume that we have a coherent control. With the coherent control, I mean that we have the ability to create any superposition that we want. That's the state psi, with some probability 0, with some probability 1, and at the same time. And we have the ability to measure the system and do it in a scaling manner. So if we have that, we can build quantum algorithm. Let's see how a quantum algorithm will look like before moving to the next step. So this is a kind of sophisticated algorithm, but don't panic. I don't want to teach you how this algorithm is working. What I want you to learn from this picture is that, so in this particular example, we want to find the eigenvalue of matrix U, which has a phase theta. We want to estimate theta. And this algorithm promised to do that efficiently. And like all other quantum algorithms, it has 3 steps. One, initialization. We assume that we can initialize the system in any state that we want. Second, we have gates. Gates are actually those interactions that I talked about in the Schrödinger equation. So we assume that we can interact with the system in a certain way, that we can implement certain gates. It's corresponding to the logical gate that we have in classical computing. And then we can measure the system. If we have all of these tools, putting them together, we can estimate theta with high efficiency. In this particular example, if you want to have a better accuracy, we have to increase the number of gates that we are applying, and that will increase the depth of the circuit. Keep that picture in mind, we'll get back to that. Okay. This is the theory of quantum algorithm in 2 slides. Now, you may wonder, okay, people always talk about qubits, 0 and 1, 0 and 1, two-level system. Once you want to build a computer, what that two-level system is, I want to see it. And I want to show it to you, how the quantum hardware looks like. Over the past 30 years, there have been numerous proposals for building a quantum computer. And so far, nobody can say this approach is better than the other one, because each one has some advantage and some disadvantage. Few examples are neutral atoms, ions that are natural, and artificial systems like superconductor qubits or quantum dots. Those are things that we engineer, Majorana fermions, and these are all two-level system quantum computing. We also have QML-based computation that Xanadu is taking, the company that I've been working for. Okay, in the upcoming slides, I want to show you what those two-level systems are in practice. For neutral atoms and ions, if you look at the energy diagram of those systems, it's quantized. The word quantum mechanics comes from. It's not any number, it's quantized, it's discrete. And the energy level, they are not evenly spaced. Therefore, you can address them individually. Now, if you had the ability to bring all the population, the probability of existence of your atom, only to the first 2 levels, then, and if you could manipulate the population within that 2-level system, then it can play the role of a qubit for you, right? So it's a good approximation. And today we have the ability of applying different electrical fields and create a kind of egg holder where at a certain location we can keep atoms. How it looks like in the lab? You have, for example, an oven that generates those atom gas, and then you shuttle them through a vacuum chamber, and then you bring them, you trap them inside a cavity, and then you apply lasers from different direction, magnetic field, And this is an example of the setup that you see in the bottom. For ions, things are, there are differences, but they're not fundamentally different. What you have is the cavity would look like that. And here, this is a true picture of 6 ions, 6 atoms that are charged. Imagine that, how delicate your device has to be. Another example for a 2-level system are superconductor qubits. Before getting there, I need to introduce you to Josephson junction, which is an electrical element. When you have two superconductors and an insulator between them, it has really nice physical properties that you don't want to learn about it today. It's messy. What it does for us is that if you have an LC circuit, only an inductor and capacitor, the energy levels are equally spaced, as you see in the left picture. But as soon as you put a Josephson junction inside that LC circuit, then you introduce a kind of nonlinearity such that the energy levels look like an atom. Why the superconductors are interesting? Because they're microscopic objects. They're not basically quantum particle, but their energy levels look like an atom, quantum. So it is behaving quantum mechanical, but it's not a quantum mechanical particle. And basically, it's an artificial atom because with engineering your circuit, you can design and manipulate these energy levels. They're not fixed like neutral atoms. And this is a real picture of the fabricated device where that triangle is basically your Josephson junction. Another 2-level system, which is the last one, I'm not going to go to the end of the list, are spins. The 2 systems that I've talked so far, they had multiple levels, and we were kind of approximately considering the first 2 levels as our qubits. But the spins are truly 2-level systems. They're little magnets that are either aligned or anti-aligned with the magnetic field that you're applying. They're truly 2-level. A few examples of that are hydrogen nuclear spin. Why hydrogen? Because you can find it in water. You can simply test it, right? And historically, in NMR quantum computing, people were using hydrogen and carbon to test quantum ideas. But NMR is not scalable, and people don't take industrial approach there, but it was great for proving principles. Another system is NV centers, that I'll talk about it in a second, and quantum dots. What is NV center? In diamond, as you know, diamond is very attractive, not because it's shiny, because it has very nice properties. So in diamond, everything is made of carbon, but occasionally, one of the carbon is missing. And occasionally, by coincidence, the nearby carbon is replaced by nitrogen. This pair of nitrogen vacancy, it turns out that it has extremely good properties that we can use them as a qubit for us. For technical people, I'll say quickly that the first 2 energy levels are in the range of 3 gigahertz, which is addressable by microwave. And if you shine the laser on diamond for a long time, then the whole population will go to the groundless state. So you can optically manipulate it, initialize it, and you can control it with microwave and magnetic field. So it's very nice. Another system is quantum dot. What is quantum dot? The word dot is that we have a little dot electron that is trapped between some electrical gates. What you have basically is a 2D electron gas, and then that is sandwiched between 2 semiconductors, like gallium arsenide or silicon. And then at the top of that, you have some, you fabricate some gates, nano-sized gates, that you apply electrical current, and with good engineering, you can trap only 1 or 2 or 3 electrons inside those islands and use them as your qubits. So this is how a qubit, which is the fundamental building block of a quantum computer, looks like. And what I want you to know about the practical side of the quantum computer is that, look, these devices are so delicate and they need special equipments. They may need vacuum chamber, they need dilute refrigerator. You've seen it on the IBM website, which is a gigantic device. And you need optical instrument, you need fabrication, we need magnetic fields, and they're mainly operating at millikelvin temperature